Welcome to the lab. As I mentioned before, we are doing experiment 15 today. It is involving sort of limiting reagents, percent yield, and stuff like that. So we're pretty close to the end here. So we're just going to finish up these last few and talk about percent yield, and then we'll kind of get into the experiment a little bit later on here. So before we kind of continue on, any questions so far on sort of what we've been doing in terms of stoichiometry problems, limiting reagent problems, how to sort of handle them? Again, like I mentioned, the way you can really tell the difference between the two types is that key that you're given the starting amounts of both of those reactants. Any questions on any of that stuff here? Okay, if there's no questions, then let's knock out this last little guy here. How many grams of copper 1 sulfide is produced when 1.8 grams of copper is reacted with 1.65 grams of sulfur? So we'll just kind of throw up a unbalanced equation here, and we'll go with something like this. Copper 1 sulfide. Something like that. All right, so why don't you give that a go and see what you come up with. Again, copper is 6555. Sulfur is 3207. Okay, so let's take a look. So same idea here. We want to make sure we have a balanced equation. So perhaps a 2 there would be good. We want to take what they gave us and convert it into moles. In this case, again, we're given the starting amounts of both reactants. So that is a key that this is a limiting reagent problem. We're going to take our 1.8 grams of copper using the molar mass there from the periodic table. We'll convert that into moles. And that will give us for copper there 1.8 divided by 65.55. And that will get us, we got there 0.0275 moles. For our sulfur, we'll do the same thing. We have 1.65 grams, and we have 3207 grams per mole. And we got 1.65 divided by 32.07 gives us something like 0.0514 moles of our sulfur in this particular case. And 6355, that's good. I wrote it wrong up here. It's 6355. All right, so we're going to basically do two separate calculations, and we want to basically figure out how much product each one would produce. So if we started with our copper there, we have 0.275 moles of copper. The relationship between copper and our product is for every 2 moles of copper, we get 1 mole of our product here. And that would get us 0.275 divided by 2, 0.1375 moles of Cu2S. We then can convert that into grams using the molar mass of that. And again, here we're trying to put the right numbers in. 6355 times 2 plus 3207 gives us something like 159, I think, 0.2 grams per mole times 0.1375 gets us something like 21.9 grams of Cu2S. And again, that would be produced from copper going to make our product. Again, to figure out if it's which one's the limiting reagent, we're going to basically do the exact same calculation, except that we're going to start with our sulfur in this case. We want to make sure we use the relationship between sulfur and our product, and in this case, it is a 1-to-1 relationship from the balanced equation. Going to give us 0.0514 moles of Cu2S. We're then going to multiply it by the molar mass there. And that would get us 514 times 159.2, about 8.18 grams. Having trouble with numbers today, apparently. 8.18 grams. There we go. Cu2S. Jeez. All right. So this is the smallest number produced. That would mean that is our theoretical yield. Also means that this would not be the right answer here. And that also means in this particular case, our sulfur is our limiting reagent, and our copper here would be our excess reagent in this particular case. First off, any questions on that calculation there? So by doing, again, these two calculations here, we're going to figure out how much product we're going to produce. Again, whichever one is producing the smallest amount will be our limiting reagent, and also that again would be our theoretical yield in that particular case. Any questions on any of that there? Okay. All right, so then let's talk about percent yield. There's really sort of three types of yields that we deal with. And whenever we sort of refer to a yield, we are referring to really products and how much products we're making. And the percent yield is important. It kind of tells us, how good or bad we sort of did the reaction. And as we will see, basically to calculate the percent yield, you take what is known as the actual yield divided by the theoretical yield, and you times it by 100%. Now, the actual yield is pretty much what it sounds like. It is actually how much product you produced when you did the reaction. So this is actually how much you produced when this reaction was done. The theoretical yield is what we've been calculating off of our sort of equations. The theoretical yield is our maximum yield. So the theoretical yield is the maximum yield from the reaction or the equation. So the theoretical yield, which again is what we sort of been calculating in a number of these examples, is really the maximum amount of product that you should produce if everything went perfect in a reaction. So everything went perfect, there was no side reactions or anything like that. That is what your theoretical yield really should be. It's basically, everything went perfect. That is exactly what you should produce as a result of this reaction. Now, we know that in life, things don't go perfect. In reactions, the same thing happens. Things can happen along the way. You could be a klutz and spill things along the way. You may lose stuff as you're doing the experiment. There might be a side reaction that maybe occurs. So not all reactions are, going to be perfect, 100% efficient. There's a lot of areas where reactions are done that, you can kind of lose some stuff along the way. And again, that's where our actual yield comes from, is really experimentally how much you actually got when you did this. Now, this number here, the actual yield, is usually given to you in the problem. So usually in these type of textbook type problems, somewhere along the way, they go, hey, you produce so many grams of this guy, or maybe you produce so many moles of this guy or something like that. So the actual yield is usually given to you. The theoretical yield, you usually have to calculate. So you would calculate the theoretical yield like we've been doing all the other stoichiometry calculations in this chapter. If it's not a limiting reagent problem, you just do it like we did it, those 4 steps. If it is a limiting reagent problem, you need to obviously determine which one's the limiting reagent and how much theoretical yield you would produce. Now, usually when we sort of calculate and put those guys together, like we talked about, we get our percent yield, which is the actual divided by the theoretical times 100%. It can never be greater than 100%. So I'll put a little asterisk next to that. That's really not true. It can be over 100%. It just means that you really screwed up somewhere. So if you get over 100%, you kind of really screwed it up there. It's not like you did 200% of the work or anything like that. So usually if you do shoot over 100%, for example, in the experiment we're going to see here in just a second, part of the process when we do the experiment is we make this solid and we filter it. And when we filter it on some filter paper and collect the solid, there's a lot of water and moisture, obviously, from the reagents that are on the filter paper. So if you were impatient when you would do this experiment, for example, and you didn't let the filter paper completely dry, you would go reweigh it. And what you're thinking is your actual yield, you're getting a lot more water weight in there and stuff like that, which should have not been there originally. So usually what it usually indicates, obviously, is if you go over 100%, you kind of screwed up. And that's a very common sort of error where people sometimes do that. When they kind of get a filter paper or something like that, they collected a sample. They really don't wait for all the water to sort of evaporate off or really get away or dry it out. And they reweigh it too quickly. And they got a lot of that water weight, which they assume is their product, but it's actually just the water that's still there. So usually you want to shoot, high 90s is good, At least over 90 is usually good. 80 is still, decent, I suppose. If you got like a 2% yield, not so good. You again probably dropped it all on the floor, I'm imagining at that point or something like that. So usually percent yield, we're looking towards 100%, not usually over 100%. Again, that usually means something went wrong. If you have a low percent yield, then the reaction obviously didn't go so well for you along the way. And as I mentioned before, most reactions, again, even though based on the equation, you should get this much product out of it, there's a lot of things that occur, as I mentioned earlier, in terms of doing the reaction that can happen. And, you usually don't see usually 100% yield. So just the simple process, for example, if you're trying to scoop out a solid that you made, when you scoop it out on like a spatula or something like that, it's going to be stuck on there. So you're going to lose some of that there. If you ever poured anything out of like a beaker or a test tube or anything like that, you can pour as much as you want. There's usually something left behind that you're going to lose. So, it's very, very rare that you could yield 100%. But again, close to 100 is sort of the goal, what you're trying to shoot for, and so forth. So to sort of demonstrate this here, if we look at one of those reactions that we dealt with earlier, and we earlier saw that in theory, which is our theoretical yield here, produce 3.65 grams. And let's just say that somebody did this reaction, and when they did it, they actually yielded 2.22 grams. You then can put it into your percent yield equation, and you get a percent yield of like 60.82%. Not probably the greatest, but things happen, I suppose. We don't usually put units on percent yield because it is a percentage, so we just deal with it in terms of a percent. Now, a couple of things about the percent yield calculation here. Here we did grams to grams, which is a very common sort of way that we calculate percent yield, because in the laboratory, or if you're doing an experiment, you usually are measuring things in grams. It doesn't necessarily have to be grams and grams. You could technically do percent yield with like moles and moles if you wanted to. As long as they're technically the same units, you pretty much could put it into this percent yield equation. It doesn't necessarily have to always be grams to grams, but very commonly we do grams to grams, because obviously when we do an experiment, those are the very common sort of numbers that we have. Any questions on that there? All right, so let's take a look at one here. And again, in terms of sig figs, we're taking 3 divided by 3. The 100 we really don't look at. So technically 60.8% would probably be the correct number in terms of significant figures on this particular example. All right, so why don't you take a second here and figure out what our percent yield is for this student. Okay, so when we look at this here, obviously they tell us this is our theoretical yield, which is 5.67. Hopefully should usually be bigger than your actual. When they do the experiment, they actually did get our 4.68. So our percent yield here, again, going to be our actual divided by the theoretical times 100%. So putting those numbers in, we got 4.68 grams divided by 5.67 grams times 100%. And I believe we got something like 82.5 there in terms of our percent yield. Not too bad. It's in the 80s at least, I suppose. Again, 3 sig figs on both of those numbers, 3 sig figs there on our answer. Any questions on that particular one? All right, let's take a look at one where you got to do a little calculation. So why don't you give this a go? We want to find the percent yield if we produce 1.5 grams of SO3 in the following reaction when we take 1 gram of oxygen and react it with excess sulfur in this reaction. So again, sulfur 3207, oxygen 16. Take a couple minutes, see what you come up with on this calculation. Okay, so let's take a look at this one. So we're looking for the percent yield. So we're definitely dealing with our percent yield equation here. So we want to make sure we have the actual or theoretical times 100%. So in this particular problem, it tells us that we did produce 1.5 grams of SO3. That is our actual yield. It's a product that is actually our actual yield. So again, like I said, usually in textbook problems, that is given to you. We do not have our theoretical yield, so we do need to do a calculation to do that. In this particular case, we're given 1 gram of O2 reacts with excess sulfur. So this type of problem here is not a limiting reagent problem. Again, we are only giving enough information to figure out the grams of our O2, not our S, right? And the other piece of information that they actually gave us was that the S was the excess reagent, right? Basically told us that the sulfur was excess. By default, what that would mean is our oxygen is our limiting reagent. So just by the way the problem is written, they actually did the limiting reagent part for us. They basically told us that the oxygen is the limiting reagent and we don't have to worry about the sulfur, and that's why we don't have any numbers given to us. So really, this is just a basic stoichiometry problem at this point. We want to figure out, starting with our 1 gram of oxygen, how many grams of our SO3 would we produce. So step 1, our equation is balanced. Step 2, we want to convert those grams into moles. Again, go into the periodic table. The molar mass of oxygen is 32 grams per mole. That's going to give us 1 divided by 32. It says something like 0.03125 moles of oxygen. We're now going to do our stoichiometry. And again, from the equations and the coefficients, we see that for every 3 moles of O2, we produce 2 moles of SO3. Again, that's our stoichiometry part from the balanced equation. We're going to use that because we are interested in how much SO3 we would produce. And we're going to put the moles of O2 on the bottom so they cancel. Moles of SO2 up on top, so SO3 on top, so they cancel ours. We end up with it. And if we do that, we're going to times that by 2 divided by 3. Going to give us something like 0.0208 moles of SO3. This is technically our theoretical yield in moles, which could be fine, but the problem is here our actual yields in grams. So we do need to convert that into grams so that everybody's in the same unit when we go into our percent yield. So we do want to do step number 4 here that we talked about. We want to go back to the periodic table. We want to figure out the molar mass of SO3, which is 3207 plus 3 times 16. That's 8007. So we're going to multiply this by 8007 grams per mole from the periodic table. Moles are going to cancel, and looks like 1.67 grams of SO3. Again, this is going to be our theoretical yield in grams. Any questions so far on that part of the calculation? Again, basic stoichiometry problems, so same 4 steps that we've been talking about. The whole chapter here is basically what we're doing. All right, so now that we got the theoretical yield, we have the actual yield given to us in the problem. We now have everything that we need to basically calculate the percent yield in this particular case. And the percent yield, again, would be our actual, which was 1.5 grams that was given to us, divided by the theoretical that we just calculated, which was 1.67 grams, times 100%. And that's going to get us a percent yield of, we'll call it 89.8%. Not too bad, got almost to 90%. Any questions on those steps? So here again, very common, these type of problems, you do have to figure out the theoretical yield. In this particular case, it was not a limiting reagent problem, so you didn't have to worry about that. And you could just do a basic stoichiometry problem. Any questions? Okay, so let's do one more here to finish it out. And a little thinking here. So think about what is given to you in this problem, what you need to find in this problem, and see how you do. So take a few minutes and then we'll talk about it. Let's see here. We have phosphorus 3097. We have fluorine, which is 19. I think that's everybody. All right, so in this case, we're actually looking for how much P4 you're going to need to start with if to produce 85 grams of this guy. If the reaction yielded 64.9%. So think about what's given to you and think about what you have to work to get back to the beginning there. Okay, so let's see how we're doing. So if you weren't really sure kind of where to begin with this problem, there's a lot going on here. So let's just sort of think about what we're trying to find, what's given to us. So we're obviously trying to find the grams of this guy. Is needed to produce 8.5 grams of PF3. This is like a actual yield that's given to us. We know it's an actual yield because this reaction is only going to yield 64.9%. So that's a percent yield that's given to us. So right off the bat, we could kind of see that we have a lot of information about percent yield that's given to us. And our percent yield, again, is our actual yield divided by our theoretical times 100%. And if we see we do have the percent yield given to us, we do have the actual yield given to us. We do not have the theoretical yield given to us, but we could find that. And what that would give us is the theoretical yield of PF3. And that would be our maximum yield there. And then we could actually use that to go backwards to this guy. So the reason we can't use the 85 grams to go backwards in this particular case is that's our actual yield based on only 64.9%. Remember that the theoretical yield is based on 100% of this reaction occurring correctly. And that allows us to figure out, in theory, how much we should start with to kind of yield that. So again, that's why we can't necessarily directly go with the 85 grams backwards to our P4 because we have this percent information. We're not going to get 100% of it to go backwards. So we have to use our percent yield really to figure out our theoretical yield first. So our theoretical yield, if we kind of multiply things across, will end up being the actual yield divided by the percent yield. They basically switch places times 100%. So that is going to get us, if we put in our numbers, actual was 85 grams. Our percent yield was 64.9% times 100%. Percentages will cancel out and leave us with grams, and we will end up with it's like 130.97 grams of PF3. Any questions on that so far? So now that we have our theoretical yield, we know that this is the maximum amount of yield that we should get. We can use that number to work our way backwards to basically figure out how much we should put in this. Even though in theory it's not going to give us 100%, but we need that starting amount to basically yield about 64% of our product in this particular reaction. So at this point, it's a basic stoichiometry problem going backwards now from PF3 to the P4. So we're going to kind of do the same steps. We already have an equation as balanced. We then want to convert this into moles, which would be our second step here. So taking our 130.97 grams of, that was PF3. We're going to convert it into moles using the molar mass of PF3. So that is 3097 plus 3 times 19 gives us 8797. Again, from the periodic table. That gives us 130.97 divided by that, 1.489 moles of PF3. Again, here we're not interested in PF3, so this is the stoichiometry part. So from the balanced equation, we could see that for every 1 mole of P4, we get 4 moles of the PF3. So for every 1 mole of P4, we get 4 moles of the PF3. Again, that's our mole to mole relationship from our balanced equation, as you can see there. So we're going to do that to allow us to get back to our phosphorus, which is what we're interested in. Again, we're going to put the 4 moles on the bottom here so that the PF3 cancels. 1 mole of P4 up on top. That gets us 0.3722. And in this particular case, we were looking for grams, so back to the periodic table. And we're going to get the molar mass of P4, which is basically 4 times 3097. Going to give us 123.9. And that is going to tell us that in this reaction, we need something like 46.1 grams of P4. So really what that number means is if we throw in there 46.1 grams of P4, this reaction will probably only go about 64% of the way there, and that will produce us whatever we got there, however many grams that was there, 85 grams instead of the 130 some odd grams. Any questions on sort of that combination step there? Our questions on stoichiometry in general, limiting reagents, excess reagents, basic stoichiometry problems, percent yield. Any questions on that?